Hi guys, I'm going to go over reading the periodic table. Again, I've had a few questions on it and I tried to record it when I was helping the students, but just wasn't working. So hopefully this helps you guys understand the periodic table if you are uncertain about it. So first of all, let's look at the periodic table. I know it's a little bit blurry, but this at least if you copied the periodic table the way you were supposed to in the video that I already gave you, this is the end product of that periodic table. So I'm going to use this to try to help explain some things. So first of all, the colors that you started with are identified up here. So we have a key. So the pinkish purple, pinkish red color that I used first, all of these are metals and they all have the same properties of a metal. So metals would have luster, which is like its shininess. They would be solid at room temperature. Of course, we do have one exception here, but that's a different color. They conduct heat and electricity. They are malleable and they are ductile. One of the questions on the rubric for the element project is, does it conduct? So if it is a metal, yes, it conducts. A metalloid is this like staircase over here that's green. Metalloids have properties of metals and nonmetals. So they are semi-conductive, for example. So if one of these elements is what you're using for your project, then for the question on the rubric, does it conduct? Is it conductive? You would say that it's a semiconductor. And then over here, these orange ones are all nonmetals and they do not conduct. And it says right here, don't conduct. So they don't conduct heat or electricity over here. You might find some under the right circumstances, the right pressure or situations that they could conduct electricity possibly, but they are not good conductors. So for our case, for right now, we are going to say that the nonmetals are not conductive. All right, the next thing we're going to look at is reactivity. So down here, we see that the line going this way, it says increasing reactivity. We have an arrow going this way. We also have an arrow going down of increasing reactivity. That would mean if we follow these arrows along, this should be the most reactive element. And then as we get away from there, the reactivity decreases. And up here, where the numbers that we circled up here with the valence electrons, that's going to prove our case with reactivity. So I had explained in the previous video, it's hard to see up here what that says. It says that all the numbers that are circled have the same number of valence electrons in that column. So all of these guys here have the number 1 circled, which means these all have 1 valence electron. These all have 2 valence electrons. We skip the transition metals because they have a different way to figure out the valence electrons. These all have 3 valence electrons. These all have 4, 5, 6, 7, and 8 valence electrons. To be happy, the element wants 8 valence electrons. So these guys over here are happy. They have the 8 valence electrons. They are not looking for more electrons to share. So they are not going to be reactive. And again, if we look at this arrow going backwards, the increasing goes this way, not this way. So these guys are not reactive at all. They very rarely will bond with another element. They don't want to. They are happy because they have their 8. These guys, however, only have 7, so they still need 1 more electron. So if we look at a common molecule that's made from a 7 plus a 1, we see sodium chloride. So Na has 1 valence electron, plus Cl has 7 valence electrons, and 1 plus 7 equals 8. So together, NaCl makes them happy. They now have 8 valence electrons total between the two of them, so they are no longer reactive. They're happy and they're calm. Another common molecule we can look at is right here. We have 6 in this column. So 6 wants 2 more. So 6 can get 2 more by doing 2 1s. It can get 2 more by getting 1 of these 2s. But let's look at a common molecule. 6, oxygen, plus 2 hydrogens, H2O, right? That's water. That is another common molecule. So this 1 plus 1, so 2 hydrogens, plus 6 equals 8. So that's where water comes from. So water will bond that way. So those would react to get that 8. So hopefully that makes a little more sense with the valence electrons. The valence electrons also tell us how many dots are going to be around our Lewis dot diagram. So for example, oxygen will have 8. Neon will have 5. Let's see, over here we have, I think that's fluorine. No, what letter is that? Oh, that's a TI. Let's see one that you guys have heard of. So gallium, for example, would have 3. So this tells me how many dots will be around my letter. These, again, you're just going to have to look that up. Transition metals, again, like I said, they do their valence electrons differently. It's not so straightforward. But any of these ones would have 2 dots. Any of these ones would have 1 dot. So let's just look that up. We'll look up lithium. We'll look up nitrogen. So lithium should have 1 dot. Nitrogen should have 5 dots. And neon should have 8 dots. All right, so lithium Lewis dot diagram, we said 1 dot, and there we go with our 1 dot. I said, I think nitrogen should have 5 dots. 1, 2, 3, 4, 5. So we have 5 dots. Some of these pictures, don't be fooled, because some of these pictures are showing them being bonded. So don't look at the ones that are bonded, look at the singular. Also make sure it's the right element. I was making that mistake earlier, looking at just B, which is boron, but trying to do bismuth, which is Bi. So I was finding the B and the dots weren't matching up, and it was because it was the wrong element. So here, this is oxygen plus nitrogen plus another oxygen, and this is how they're combined. So don't look at this. Make sure you're looking at just the nitrogen by itself. And then the last one I said, we'll look at neon. Neon is in the last column. That's a noble gas, so that should have 8. And here we have 2, 4, 6, 8. All right, so you should be able, unless you are doing one of the transition metals, you should be able to figure out how to do the Lewis dot diagram correctly based on your periodic table. Let me get that picture up again. All right, so we understand valence electrons, we understand reactivity, we understand how to use the valence electrons to make our Lewis dot diagram. The next one we're going to do is let's talk about the Bohr model. So for the project, you also have to have a Bohr model. And the Bohr model is the one where it's drawn out, where you have the rings around the nucleus. So the nucleus we identify by our protons and our neutrons. So remember, our protons are the atomic number. So whatever number, whole number, is inside of the box, that is our number of protons. It also is our number of electrons. So that's how many electrons are going to be in the rings. Over here, the atomic mass, that is our neutrons plus our protons. And we already went over how to find our neutrons. So neutrons plus protons, to find neutrons by themselves, you take away the protons. So you round up this decimal. So for boron, for example, it's 10.811. So if we round that to the closest whole number, it would be 11. Our number of protons is 5. So we take the 5 away from the 11, and we're left with 6 neutrons. So 6 would be our number of neutrons for boron. 5 would be our number of protons for boron. That would be what goes in the middle. And then 5 electrons would be on the outside. Our periods are what will tell us how many rings there needs to be for the electrons to be on. So our periods, that is one of the questions on on the rubric for your project. So our periods are here: 1, 2, 3, 4, 5, 6, 7. And remember that these two fit up in here, which means this is in period 6 and this whole row is in period 7. So this tells us how many rings there are around our atom. So let's look at right here, potassium, for example, the letter K. That should have 4 rings. It should have 19 electrons. And now the number of electrons you put on each ring is very important also. So the first ring has to have 2. The second ring can go up to 8. And then the third and continuing past the third and fourth ring and so on up to 7 rings, those actually depend on the, it depends on a few things. So if you have anything bigger than neon, number 10, so again, that would bring us to the third ring, then you can look at at Google for an image. So potassium, we know that there's going to be 4 rings because it's in period 4. The first ring is going to have 2. The second ring is going to have 8. That will get us to 10. And then the third ring and fourth ring, we're going to look up to see how many they say it's going to be. So we're going to look up potassium. All right, so again, I said 4. So 1, 2, 3, 4. Our first ring has to have 2, and there's 1, 2 here. Our second ring has to have 8, 2, 4, 6, 8. Our third ring has 2, 4, 6, 8 around it also for this one. And then our fourth ring has that one extra that we need. So 2 plus 8 is 10, plus another 8 is 18, and then 19. So again, here's another way you could do it. And I don't care which order you do it, you just have to have the right number. So the first ring, so 1, 2, 3, 4 rings. First ring has 2, second ring has 8, third ring has 8, fourth ring has 1. All right, so hopefully this is a little bit more clear. Let's just look up another one really quickly. So let's look at that picture again. Let's pull up, how about, okay, a lot of people are doing krypton. So let's do krypton. So if I go over, oh, krypton's going to have 4 again. Let's do a different one. Let's go down, radon. All right, so radon, if I go over, radon has 6. So radon is in period 6, which means it's going to have 6 rings around it. It is going to have, again, the 2 and then the 8. Those are the 2 that I'm really concerned about. And then you're just going to look up, because it's such a big number, we're going to be looking up the Bohr model. But we know that it has to have at least 6 rings. 2 are on the first ring, 8 is in the next ring. And then past that, we're going to see what they come up with. And some pictures are going to be different. So you can just choose the one that you like the best. So radon. So we're looking for 6. 1, 2, 3, 4, 5. I missed that first ring. So that's 6. All right. So again, 1, 2, 3, 4, 5, 6. All right. So you guys see where the 6, period 6. So we know that both of these are correct. Radon, because the number is so big, I'm not looking for you to draw out 86 protons and 136 neutrons. You can actually do it just like this. So anything past 10, any element bigger than neon, you can make your nucleus look like this, but the electrons you have to draw out. All right, so we have the first ring. I kind of like when the electrons are spread out, not next to each other like this one is, but this one does look pretty too. So whichever one you like to draw is fine with me. But here we have the first ring has 2. The second ring has 1, 2, 3, 4, 5, 6, 7, 8. And then past that, remember that potassium had 8. But radon has a whole lot more than 8. So again, it's going to depend on which one you want to go with, and I'm okay with whatever you want to. That's more of a high school or college level with understanding how many electrons go on the ring. So we are just going to understand the first 2 rings. First ring always has 2, second ring always has 8. And then past that, it depends on the element. All right, so hopefully that helped you understand how to do the Bohr model. So you should be able to identify a correct Bohr model now when you're looking them up. The next thing we're going to do, actually, that's pretty much everything that you would need to know for this project. So again, if you have a transition metal, one of these, your Bohr model and your Lewis dot diagram, you're most likely going to have to look up and go by whatever you find for there. If you need help, please let me know. Otherwise, you should, if you're in 1 or 2 or 13 through 18, those you should be able to do, at least for the Lewis dot diagram, you should be able to do on your own. For the Bohr model, if they're bigger than 10, like I said, you're probably going to have to look that up to help you out with the 3rd, 4th, 5th ring, 6th ring, 7th ring. The last thing I wanted to go over was the groups or the family. So another question on the rubric is what group does it belong to, or what family does it belong to? And group and family are interchangeable. It says right up here that this is either the group or the family, and they share the same physical properties, which means, again, it goes with the valence electrons. This group right here, this is a family. They have the same physical properties, just like anybody that you are biologically related to. You would share similar properties. They all have 1 valence electron, so they are highly reactive. They are all in the metal group, so they are all metals. They want 7 more valence electrons. And they have a special name, so we named them down here, alkali metals. The second group here, they have a special name. They are the alkaline earth metals. All right, these guys are all transition metals, but they have their own families also. So this row, they don't have a special name down here, so we're just going to call them group 3. I mean, this column. This column doesn't have a special name. They're group 4, group 5, group 6, group 7, group 8, group 9, group 10, group 11, group 12. Group 13 through 16, they can be group 13 through 16, or we can name them, a lot of times they're referred to by the first element in their group. So this is the boron group or boron family, the carbon family, the nitrogen family, the oxygen family. These guys have a special name again. This is the halogen family. These are the noble gases. Okay, so hopefully now you guys understand a little bit more on how to read the periodic table and how to complete the project. Before we move on, I just want to go over the rubric, which is found on the website, just so that you understand what you should be doing with each section. Bohr model, Lewis dot diagram, I think I explained that enough. The picture. So a picture that you're going to include is either a picture of the element, like if you're doing gold, you can easily find a picture of gold, or a picture of the element in use. If you're doing something like oxygen, where it's a gas, we can't take a picture of that because it's clear. So you need to find a different way to represent oxygen. So you can do like an oxygen tank, or you can do a picture of the sky with the O2s in it, and that would be oxygen. If you're doing helium, for example, again, that's another gas. Instead of you can't do a picture of a gas, but you can do a picture of a helium tank, or you can do a picture of a balloon. So be creative. If you can't see your picture, if you can't see your element, be creative with how you display it, but a picture needs to be on there. Density, that is a number that's going to come up. We have radon here already, so let's go ahead and look up the density of radon. It's going to be a number that's going to be grams per centimeter cubed. If it's a liquid, it'll be grams per liter. And let's look at all. All right, and the number comes up right here. So this is kilograms per meter cubed. We haven't talked about conversions yet, so you can use these numbers if you want to. So this is what your density is going to be. It's just going to pop right up. Should be very easy to find. Reactivity. We now understand when we're looking at our periodic table how to identify if it's reactive or not. Remember column 18, our noble gases, they're happy. They have 8 valence electrons. They are not reactive. All the other ones are reactive, and they get more reactive as you get closer to the first column. So this is a yes or no question, and you're going to find it on the periodic table. Abundance on Earth, you look it up. Sometimes you might need to search a little bit. And it's just going to be a number. So here we have, this is the percent of radon in the Earth's atmosphere. You might be able to do a little bit more searching to find if there's radon in the crust of the Earth or deeper in the Earth. So do a little research on it. Color, if it's a gas, it's going to be clear. Otherwise, you need to look up the color of your element. Just find out what color it is. Some elements have multiple colors. So for example, carbon is in the form of a diamond. So you need to give me all the colors that it can be when it's a diamond. What color is it when it's coal? What color is it when it's graphite? So you might need to do multiple colors. Is it a metal, nonmetal, or metalloid? Again, based on the way you colored your periodic table, you should be able to identify that. Conductivity. Again, if it's a metal, it says right here that it's conductive. If it is a metalloid, it is semiconductive. And if it's a non-metal, it is not conductive. Shape at room temperature. If it is a solid, you have to look this up. If it's a solid, you need to determine, is it an amorphous solid or a crystalline solid? And that's a little research. Again, sometimes you might need to, depending on the element that you have, you might need to actually read a little bit to find the answer. If it's a liquid, then it's a liquid. It's not a solid. If it's a gas, same thing. It's not a solid, so you don't need to tell me if it's an amorphous or crystalline structure because it's a gas. But you do need to say which shape it is at room temperature. Then you're going to identify the element. So the symbol has to be part of your project, the atomic number, the atomic mass, the number of protons, electrons, and neutrons. Again, all of that is going to be found inside of the box on the periodic table. Very straightforward, super easy. If you don't remember how to identify it, you should have already taken notes, which is on the inside here. We did it for boron. The period it's found in. Remember, if I write a sentence, at the end, I put my period. So my periods go this way. I also wrote it down here, or you should have written it down here, that these are your periods. Your family or group that it belongs to are the rows. And again, up here, it says that the group or family, and they share the same properties. So you're telling me which family it belongs to. Remember, some of them have special names. Alkali metals, alkaline earth, boron, carbon, nitrogen, oxygen, halogens, and noble gases. If it's one of these guys, they also have special names. These are the lanthanoid series, and this is in the actinoid series. So you need to identify that. 5 interesting facts. Look them up online. 5 ways you relate to the element. Those are ways that you have all told me already that you already have them. So you guys should be okay with that. You understand that. And then creativity, neat, and presentation. That's just part of your project. So hopefully this helps clarify a few things. Hopefully you guys are okay. But if you have questions, please let me know.